All right. So Rowena has been a PhD student, or is a PhD student, PhD candidate, at the Grasslands node in Pietermaritzburg. And she's been working on a lovely cross-disciplinary project, a merger between hydro and soil science. And yeah, so I think that's pretty exciting. And let's see what she has to say. I'll let her introduce the title of her talk. I'm sure you will have read it. But yeah, let's go ahead. Over to you, Rowena. Thanks.
Thanks so much, Paul. I'll just share my screen. Sorry. Okay, can everybody see it?
Coming through clearly, my side.
Great. Oops, sorry. Okay, yeah, thank you so much, Paul, for the introduction. And thank you to everyone for the opportunity to talk to you today about my PhD. So my talk is on one part of my PhD, and it's on gaining insights into the hydropedological character of 3 Afromontane catchments within the Cathedral Peak area. So just as a background, so I'm looking at the interactions of dissolved organic carbon and hydropedology in the Cathedral Peak research catchments. So what is hydropedology? It's a branch of soil science that studies the movement and attenuation of water within soils. So what it does is it looks at how do soils affect water movement, and how does water affect soil development. Then again, what is dissolved organic carbon? So it's the organic matter that is able to pass through filters between 0.22 and 0.7 micrometers. That's really tiny. So the reason for my research is that in order to address current and future water resource challenges, we need to improve our understanding of complex relationships between different soil properties, land use management, and the hydrological cycle. When I was doing a literature review for my PhD, I found that a lot of the studies on this topic are based in the Northern Hemisphere, in the temperate zone. And then a lot of them are also based in forest ecosystems. So one of the aims of my PhD are to understand or improve our understanding of DOC fluxes within mountainous areas here in South Africa, as well as within grassland ecosystems. Okay, so I'm working in the Cathedral Peak area. I think most of you know where it is. So it's on the border between Lesotho and KZN. There are 15 research catchments in all, but I'm looking at 3 of them. So catchment 3, catchment 6, and catchment 9. So this is the top of the catchment, and then it drops in altitude that way. Again with catchment 6, top of the catchment, down towards the weir at the base here. And catchment 9 has a different aspect. So this is the top of the catchment here, and then it moves in that direction. Just as a background to the catchments, catchment 3 is known as a degraded catchment. This is because there was a forestry experiment in which pines were planted in the catchment in the 1950s and 60s. The trees were removed in the 1980s, and the catchment, they tried to rehabilitate it with Eragrostis curvula, which is a grass species, but there's still a lot of erosion throughout the catchment area. There's also a lot of bracken and bramble, which are both invasive species, and these species have caused quite a lot of basal cover within the catchment area. Going on to catchment 6, this is known as the core catchment of all the research catchments. And that's because there's quite a focused and detailed monitoring ongoing in this catchment area. So there's a lot of data gathering for evaporation, for soil moisture, for groundwater monitoring and carbon flux monitoring. The catchment is a mesic grassland, and it's burned by NND during spring. And then finally, catchment 9. So as I said before, it's located in a different aspect to catchment 3 and 6. 3 and 6 have a north-northwest aspect, whereas catchment 9 has an east-northeast aspect. The catchment's been completely protected from fire since 1952, but it has experienced some wildfires and some accidental fires throughout the years. But as a result of the fire exclusion, this catchment is dominated by woody scrub, in particular the Leucocidia and Buddleia species. So just some images of what the catchments look like. This is catchment 3. This is the weir and the outlet of the catchment. As you can see, it's quite degraded. Up on the hill slopes here, doesn't really look like it in the picture, but it is covered in bracken and brambles, and there is quite a low basal cover. Catchment 6, this is looking from about the mid-catchment down towards the weir at the base here. As you can see, it's a good quality grassland. And then catchment 9, this is quite a woody catchment compared to catchments 3 and 6 as a result of that fire exclusion. Okay, so one of the core aspects that I wanted to look at firstly was, how does water move within these catchments? Because once you understand how water moves, then you can understand how carbon moves. And in particular, I wanted to look at how does water movement relate to the soils of the catchments. So the first thing I wanted to do was create a hydropedological soil group map for each of the 3 catchment areas. And we decided to go with a digital soil mapping approach. So what is digital soil mapping? So what it is it's a tool to interpret the spatial and temporal soil properties of an area, and it uses certain mathematical models to do this. And these mathematical models are based on quantitative relationships between environmental information and certain soil measurements. So we use what's known as the Arc Soil Inference Engine, or ArcSIE. This is a tool which is an extension of ArcMap. And this tool generates soil maps based on the soil environment model. That soil is a function of its environment. So it creates soil maps according to existing relationships between certain soil attributes and how those are related to certain landforms. It also creates maps based on what's known as the fuzzy logic. And fuzzy logic takes into account the complex nature of soils. So it tries to create a more gradual and continuous change between one soil group and another soil group in a map. So what does this all mean? So as you can see in this conventional polygon-based map, there's an abrupt boundary between one soil group and another. But in reality, this is not true. There's always a more gradual and continuous change from one soil group to another. There's never an abrupt boundary between one group and another in nature. So what fuzzy logic attempts to do is attempts to break up this boundary and create a more gradual boundary between one element and the next. So the first thing we did was we took the existing soil maps for catchment 6 and catchment 3, and these were created by the Soil Science Association of South Africa. And then we created another map for catchment 9. And all 3 maps were classified as per the South African soil classification system. I then took the soil names and I regrouped them into hydropedological soil types. This is also based on the South African hydropedology system. And there are 4 different groups. So firstly, you get the shallow recharge soils. So these are freely drained soils, but they're shallow in nature, less than 500 millimeters deep. And for those of you who know soil types, these include the Nomancy and Misper soils. So the Nomancy and all the rest of the soils you'll see are humic soils. So we're working in quite an organic area. Then you get the deep recharge soils. So these are similar to the shallow recharge soils, they're just deeper profiles. So they're greater than 500 millimeters. Then you get the interflow soils. So these have a freely drained upper horizon which overlies relatively impermeable bedrock. And at this interface, the soils show hydromorphic properties, which signify periodic saturation associated with the water table. And then finally, you get the saturated responsive soils. So these were found in the permanently saturated wetlands, and they display indications of long-term saturation. So for example, the champagne and cut spread soils. Okay, so ArcSIE consists of two different components. You get a rules-based approach, and then you also get a case-based approach. So we first started with the rules-based approach. So what we did was we applied rules to ArcSIE, and these were based on the outcome of various digital terrain models that we created, as well as our own knowledge of the catchment areas. And the digital terrain models that we created included the wetness index, the slope, the elevation, and the planform curvature. So this table is just an example of one of the catchments, catchment 3. So as you can see, we classified each hydropedological soil group, and then we related it to each digital terrain model. So for example, the recharged shallow soils, these occur within areas of a wetness index of less than 1, so within quite dry areas. They occur high up in the catchment area, and they occur on quite steep slopes, slopes steeper than 30%, and then they also occur on convex slopes. So as you can see, the recharge deep, similar factors, and then the wetness index obviously increases as you get the more wet profiles, with the responsive saturated soils occurring in the wettest area. Again, they can occur throughout the catchment area, but on much gentler slopes and also on concave slopes. So we use these tables for catchment 3, 6, and 9 to produce the optimal curves that describe quantitatively the relationship between the soil group and the particular digital terrain model. So once we had identified all of these for each catchment, we then set all these values into what's called continuous function curves, and those are set by ArcSIE, and they help to precisely define each parameter for the soil group. So for example, you get, these are the different curves that you can put into ArcSIE. So for example, a bell-shaped curve. So this soil in particular is an interflow soil for one of the catchments, and it's optimally occurs between slopes of 15 and 25%. This recharged shallow soil optimally occurs between slopes that are greater than 30%. And this responsive saturated soil optimally occurs on slopes gentler than 21%. So we did this for every single soil type, for every single digital terrain model, and for every single catchment. And once we had put all that data into the ArcSIE Inference Engine, we got maps that look like this. So this is catchment 3, just as an example. So I produced one map for the recharged shallow group, one map for the recharged deep, for the interflow, and then also for the responsive saturated soils. And then what's nice thing about this program is that you can combine all these maps optimally, and it creates a final map for you of the hydropedological soil group for catchment 3. But we had a look at the map and we realized that it wasn't really that accurate. There's far too much interflow soils, and then you can't really see any recharged shallow soils, which we knew from being in the catchments that this just wasn't true. So we decided to refine the maps, and we used a case-based approach. So what a case-based approach is that it uses case-based features to adjust the predictive models. And this helps you to better reflect your knowledge about the particular landscape. So what we did was we took the existing soil maps and the existing soil information that we had, and then we added these as individual cases to the ArcSIE interface. So these are the individual soil types that we knew existed. So for example, in catchment 3, and then catchment 6 and catchment 9, we had specific soil points that we could add to the inference engine. And then we refined the maps according to these validation points. And then these are the final maps that we got, far more accurate than the original maps. So I think they came out quite nicely. You can see the rocky outcrops at the top of catchment 3, where the recharged shallow soils are, shows the streams and wetlands within the catchment. Catchment 6, a lot wetter catchment than catchment 3. Again, it shows where the rocky outcrops are, which is accurate. And then catchment 9 shows where the streams and wetlands are and the rocky outcrops and the recharged deep soils in between. So we wanted to check our agreements between the predicted maps and then also where we had specific ground truth points. So we used the Kappa coefficient of agreement. And so C3 came out at 0.57, which is a weak correlation. C6 also a weak correlation, and C9 a moderate correlation. So this might not seem too good, but it is in line with various similar studies that have been conducted. Most studies that do this similar type of work all get these types of correlations. So what we found out was that the quality of the soil group maps that we created are very much determined by the method that you use. So if you only use a rule-based approach, it won't be as accurate as if you can put in case-based features to validate the maps. And then also it's very important to use high-quality digital terrain models for the model predictions. So even though it came out as weak and moderate, I feel the map still achieved an appropriate representation of what is really happening in the catchments, far more accurate than a polygon-based map where there are abrupt boundaries. Of importance is that the accuracies and inaccuracies of the maps can be quantified, and this allows you to use a confidence rating in the use of the maps in further applications. So what we learned is that ArcSIE is a powerful tool, especially if you want to gain a general idea of the relationship between the soils and the landscape, and you don't need very specific information. But if you do want, if you do want specific information, then the knowledge of the soil-landscape relationship, as with the traditional soil mapping exercise, is still necessary to improve the accuracy of the tool. Okay, so once we had created our soil maps, we then wanted to use them in hydrological modeling. So we wanted to do this in order to understand the hydropedological behavior of soils within the 3 catchments. And we used a SWAT plus modeling tool. So in the SWAT plus modeling tool, I used the maps that we had created. I also used different soil data that I collected. And then I also used certain measured hydrograph and soil water content data that was collected in catchment 6 in the 1990s, but which was published in 2007 by Kuneni. So what Kuneni did was that he created drainage curves for the dominant soil types of catchment 6. And these curves were created from measuring the soil water content at certain time intervals. So he saturated a profile, and then he measured the water content at specific intervals until the profile became dry. So the soil water content was measured using neutron water meter access tubes. And he did this for a period of 4 years along a 200-meter transect for 3 different soil types. So the soils were representing deep soils, moderately deep soils, and shallow soils. And then he used the volumetric water content versus time data to construct a drainage curve for that particular profile. He did that for each profile. And this is one of the curves that he created. I won't go into it in any detail. But what he did find out is that the main components of stream flow in catchment 6 are attributed to overland flow as well as subsurface flow through the soil profile. And what he was able to do is create a series of time steps in days that shows how water flows through the catchment and through certain soil profiles before it contributes to stream flow. So we knew we could use our soil information along with their soil information and put that into a hydrological model and hopefully improve the hydrological modeling accuracy. So we hypothesized that the data could be transferred to the lateral time it takes for each hydropedological soil group to contribute to the stream flow. So what is lateral time? So lateral time is the measure of the time required for water to flow through the catchments before being discharged into the stream. So it is very dependent on the types of soils that you get in a catchment, as well as the location of soils in relation to the stream. So what we did was we wanted to set the lateral time within the SWAT model for each hydropedological soil group. And using his drainage curve, we came up with these time series. So for recharged shallow soils, it takes about 6 days for water to infiltrate that profile and then make its way to the stream. Recharged deep soils, it takes about 24 days. The interflow soils, it takes 65 days. And the saturated responsive soils, it takes 85 days. So water is far more attenuated in these saturated responsive soils before it's being discharged into the stream. So we set up 2 exact models comparing the default lateral time and with specific lateral time inputs that we put into the model. And the specific lateral time inputs were based on the location of a hydrological response unit created by SWAT within the hydropedological soil group map. So what this means is that SWAT, when you set up the model, it produces, so this is for catchment 6, it produces different hydrological response units. So it divides the catchment up into different hydrological response units. And this is just zooming in on that. So we overlaid that map with our hydropedological soil group map. And then we were able to see where each hydrological response unit sits in relation to a soil group. So for example, hydrological response unit 35 sits on an interflow soil. And then we were able to take that information and manually input it into the SWAT model. And then we measured both simulation runs, so the default run where we didn't input any lateral time, and then the specific lat time run against observed stream flow for each catchment. And this is what we got. So this is for catchment 6. We created a graph showing a correlation between the specific lateral time, which is the red line, the observed flow, which is the blue line, and the default simulated flow, which is the green line. So yeah, for catchment 6 over a period of 5 years. So as you can see, the blue and red lines follow each other a lot more closely than the green line. And of importance is that you don't get these spikes, which you do in the green line of peak flows. And these spikes just, they're not accurate. And then what we also did was we created flow duration curves for each of the catchments. So flow duration curve is a cumulative frequency curve that shows the percentage of time during which the observed stream flow, so the blue line, is equaled or exceeded by the simulation runs that you are comparing it to over a given time period. So what you can see is that the blue and red lines are far more correlated than this green line. And then for catchment 3, we got very similar results. The blue and red line following each other much more closely than the green line, and we're not getting these peaks. So unfortunately, there was quite a few data missing for catchment 3. There were some issues with the instrumentation. And then there was also a large fire in catchment 2 in 2019, which caused the weir to silt up. So we didn't get a lot of information for about a year in 2019 to 2020. So what we did was we also ran the model using historical time data, just to show that it does work for both time series. And then, yeah, we also did the flow duration curve for catchment 3. Again, the red and blue lines are more correlated than the green line. And then finally, for catchment 9, same thing as the other two catchments, red and blue line following each other a lot more closely than the green line, and it doesn't give these dramatic peaks, which are not a reflection of what is really happening in the catchment. Same thing with the flow duration curve, yeah, red and blue line following each other. Okay, so then we wanted to do some model validation. So the statistics that we used are the coefficient of variation, or R squared, the percent bias, the standard deviation, the Nash-Sutcliffe efficiency, and then the alternative metric to the Nash-Sutcliffe efficiency, which is called the Kling-Gupta efficiency. And the specific lateral time inputs improved modeling accuracy in all the statistical parameters that we used. So these are just some examples if you want to have a look. And then what we found out is that the ability to define the specific lateral time for each hydrological response unit was seen as a beneficial input for this SWAT model, and it helped us to improve our understanding of the catchment's dynamics. So what we found out was that the distribution of the hydroped soil groups played a large role in how precipitation flows through the catchment. Is it overland flow? Does it infiltrate into the soil profile before reaching the stream? How does it move through various areas of the catchment? And also, how does it influence the stream flow? So, for example, catchment 9 had a greater distribution of soils in the recharge shallow group as compared to catchments 3 and 6. So you would expect a quicker distribution of water from the top of this catchment to the stream flow. So you can't use the same information from catchment 3 and 6 and 9. You can't use the same soil input into the SWAT model, even though the soils are very similar, because they all react differently to how water moves in the catchment. And then when you look within a catchment, you have catchment 6, and this has a greater combined percentage of soils in the interflow and responsive saturated groups. So you would expect a longer lateral time taken for water to move through these soils before it contributes to stream flow. So we felt that in the end, soil information should be coupled with the ecological information that you put into the SWAT model, such as the effects of fire, the effects of vegetation and different land cover, as well as the rates of evapotranspiration on the hydrological modeling accuracy. And these aspects have all been shown to be interrelated. We definitely need more integrative studies requiring both specialists within the field as well as collaborative efforts across disciplines. And we found that the use of soil hydraulic properties within hydrology models can help one to understand how precipitation moves in a catchment. So what happens to that precipitation? Does it become evaporation? Does it become infiltration or transpiration? Or does it become recharge, where it recharges the groundwater? Or is it just runoff and straight into the stream? And then in conclusion, readily available soil information is increasingly being sought after as the importance of soil and ecosystem management is more widely recognized. In terms of the digital soil mapping that I did, I found it to be hugely beneficial. And I think that it can be enhanced for larger areas where we can do soil mapping on a much larger area in competitive budgets and competitive timeframes. So the study, the SWAT Plus study, highlighted that relevant soil information based on reliable site-specific data is essential in hydrological modeling if you want to improve the accuracy of the model. And then what I'm doing so far with this information that I've gained, so I'm currently working on the environmental and physical characteristics of the catchments and how these influence the dissolved organic carbon movements and storage. And there are indications that land cover, as well as the hydropedological soil group, these do have an influence on the quantity of DOC concentrations within the catchments. But I think that's a story for another time. Thank you so much for listening.
Thanks so much, Rowena. She'll be fielding a few questions or some questions. So if anyone has a question, could you raise your hand, unmute, or there's also the chat box where you can pop your questions into. Yeah. Any questions for Rowena? I've got a question for her. I don't see any hands raised. Yeah, Rowena, just thanks again for the presentation. It's very informative, especially I'm not a hydrologist, so it's a good insight into what's happening in terms of the hydrological modeling of the catchments, and lovely to see the cross-disciplinary aspect of the project. In my experience, I mostly hear hydrologists talking about ACRU and ACRU modeling. Could you explain the difference? Because I see you used a SWAT model. What is the difference, and why did you go with the SWAT for that?
Thanks, Paul. Yeah, I'm not a hydrologist at all either. Definitely a soil scientist. So to be honest, I don't know the difference between ACRU and SWAT. I know ACRU, I think it's used quite a bit in agricultural landscapes, but I could be wrong. We went with SWAT Plus because it gave you the option of inputting the specific lateral time, which was the main aim of our study, and it it was quite easy for us to input that specific lateral time. So that's why we chose SWAT. I don't know anything about ACRU, to be honest, but I do know that hydrologists, they do really like it. It would be a good study maybe in the future to compare the results with an ACRU run of the models using this similar inputs.
Thanks, Rowena. Yeah, I was wondering whether ACRU wasn't spatially explicit like SWAT was, like the cell by cell application,
yeah,
but I can't answer that.
I don't know if anyone else is a hydrologist that's listening.
Yeah. I don't see any other hands raised. In terms of something that's like in the back of my mind that's potentially interesting with this is, do you think it has potential to influence policy, like in the Drakensberg, where trees are planted and not, because of the importance of the catchment area for water production? Do you feel that your model has enhanced like the knowledge of how, like where trees should be planted or not planted in a landscape?
I think definitely, yeah, the soil information is, when you put it into SWAT, it is coupled with the land cover, and it all makes a difference in the simulation run, and how it affects the stream flow. So for example, for catchment 9, I had to input that there were more trees in that catchment as compared to catchment 6 and 3. And then it did adjust the model for that type of land cover. So yeah, it definitely would make a difference in terms of where to plant trees, where not to plant trees, and how that affects the stream flow. And also in terms of the, knowing where the saturated responsive soils are, knowing where the interflow soils are, and also knowing that trees, suck up more water than grasses, for example. Maybe knowing the type of tree to plant in an interflow soil, for example, so that it doesn't affect the water table so dramatically, versus, planting them in a recharge deep area. I think it definitely could be very beneficial.
Thanks, Rowena. Yeah, it really does sound like it has potential to influence policy like that. Yeah, any other questions from the audience at this stage? Otherwise, I think we're going to call it a morning. Yeah, thanks very much, Rowena, for taking the time to present. You've put a lot of work into a short presentation, so well done. And yeah, all the best with the rest of your studies. I know it's coming to a close soon. So wishing you all the best and well done for doing well so far.
Thank you so much, Paul. Thanks everyone for listening.
Thanks everyone.